Okay. In the last two classes, we derive formulas for derivative while Taylor expansions. Actually, we can obtain formulas from polynomial interpolation. Today, I show you one example about how to obtain numerical formulas for derivative from polynomial interpolation. Here, suppose we are given a table of some function values of function f. Then the polynomial that interpolates this table is, say, in Lagrange form. The polynomial in Lagrange form that interpolate this table is P is equal to f x0 times cardinal function L0 plus x1 cardinal function L1 and so on. The error, how far this P is from the function f, the error is the error term. Let me see. The error term is 1 over n plus 1 factorial derivative n plus 1 times and evaluate at some point psi. The point, of course, depends on x. And then times wx, where wx is x minus x0 times x minus x1, and so on. And psi of x is between x minimum. By this notation, I mean the smallest number of x0, x1, xn, and x. X max, by this notation, I mean maximum of these n plus 2 numbers. Yeah. Okay. All right, now this is a polynomial interpolation. Now I take derivative on the both sides of this equation. Okay. Take derivative. How about next page? Take derivative on the both sides. The error derivative psi of x wx. P is this one. P is given by here. Now take derivative. F of x0 constant. This is a constant. So actually, this is equals to f x0 cardinal function derivative plus f x1 f xn, and then plus n plus 1 factorial. How to compute this derivative? Product rule. This is a take derivative on the first function, derivative on the first function, right? Then times the second function plus derivative on the second function, psi x derivative on the second function. Okay, now suppose we want to evaluate derivative at some looked xk, okay, where xk is looked, okay. That means that xk is one of these numbers. Suppose, okay. Then I plug in xk, this looked, in this equation. I have how about let me use a sigma notation. Yeah, sigma notation. This sum, let me write it in sigma notation. It is a summation I from 0 to n f xi cardinal function I derivative evaluate at xk, then plus n plus 1 derivative sine x w xk plus n plus 1 factorial. Plug in xk in x, so sine xk and then derivative wx, compute derivative on w, then plug in xk in x. Yeah. Because w its definition is x minus x0, x minus x1, and so on, x minus xk. Now x minus xn. Now I assume xk is one of the loops, so we have w xk is 0, right? Xk, there is a one factor here, x minus xk. When I plug in xk in x, then the factor is 0. So w, the value at xk is 0. Therefore, this is 0. So this term is 0. Then let me compare this derivative in detail. W is x minus x0, x minus x1. Okay, take derivative on the first factor. We get this product rule plus take derivative on the second factor, then we get x minus x0. Second factor derivative is 1, so the next factor is x minus 2, x minus xn, and so on. Take derivative on the third factor, right, and so on. Yeah, product formula, and derivative on the last factor. So the last factor derivative is 1. This is the derivative of W. Now plug in xk. Plug in xk. So when I plug in xk, all the terms are zeros except the term that doesn't involve xk. So actually, this is a xk minus x0, xk minus xk minus 1, the term that doesn't involve xk, xk minus xk plus 1, and so on. Xk m minus 1. So this guy actually is equal to the product of xk minus x, say according to my notes, xj, where j is from 0 to n, but j not equal to k, right? Therefore, from this equation, we have derivative of the function f at xk at this loop is equal to summation I from 0 to n f xi times derivative on the cardinal function li evaluate at xk. Then plus, let me see, this term is 0, and then plus this term. This term derivative on w plug in xk, then is this. So therefore, we have 1 over n plus 1 factorial. Psi depends on xk, then times the product j from 0 to n, but j not equal to k. Xk minus xj. Yeah. Then draw the error term. We have a formula to compute derivative of the function f at some loop xk. Yeah. There is a one special case. Okay, special case. In this formula, in this equation, the loops may not be equally spaced. Now let me consider the case where the loops are equally spaced. Say suppose the space size is h. That means that okay, x0, x1, x2, xn. The distance between adjacent loops is h. This is h. The distance is h. Suppose the loops are equally spaced. Then we can further simplify this equation. Then in this special case, then x1 is x0 plus h, 1 times h. X2 is x0 plus 2 times h. Xi is x0 plus I times h in this special case. Now I plug in this xi in the error term. Okay, in the error term. Then let me name this equation equation 1. Then equation 1 can be simplified as follows. Becomes derivative at xk is equal to summation I from 0 to n xi li derivative xk, then plug in 1 over n plus 1 factorial. Yeah, and then times j from 0 to n, but j not equal to k. Let me see. In this case, xk minus xj. By this equation, it is x0 plus k times h minus xj is x0 minus plus jh. Now cancel x0, then k minus j times h. So here is k minus j times h. From 0 to n, but from 0 to n, but skip k. Here, how many h? N h. So the formula can be simplified as I can take out h, n, right here. There are n, h. So hn over n plus 1. Sine k, then times a constant, doesn't depend on h. This is a constant. So this formula is order n formula. This is order n formula. The error, I can write the error as BOHN. BOHN. This is an order n formula. Yeah, we can derive derivative formulas from polynomial interpolation. Let me show you 2 examples about this equation. Say, for example, example 1. When n is 2, x0, x1, x2. Okay, when n is 2, and k is 1. That means that we want to, we have, in this example, we have three nodes. Now, suppose we want to evaluate derivative at the middle node. We want to find derivative at x1. Okay, what is that? Okay, then by this formula, in this case, let me simplify this formula. Let me name this equation 2. Then in this case, what is equation 2? Okay, what is equation 2? Solution. Cardinal function x0, L0 is, in this case, is x minus x1, x minus x2, then over denominator plug in x0 in x. A cardinal function L1, it is a x minus x0, x minus x2. For the denominator, plug in x1 in the numerator to get denominator. x1 minus x0, x1 minus x2. Then cardinal function L2. L2, it is x minus x0, x minus x1. For the denominator, plug in x2 in x to get the denominator. In equation 2, we need to compare derivative on cardinal function. Then derivative on L0 is polynomial of degree 2. Take derivative on it, we get 2x minus x1, x2 over x0, x1. Derivative on L1 is 2x minus x0 minus x2 over the denominator, it is a constant. Derivative on L2, very similar in structure. 2x minus x0 minus x1, then over denominator, it is a constant. Okay, now xk here is x1. Now I plug in x1, then L0 x1, plug in x1, then cancel 1 x1, then I get x1 minus x2. Plug in x1. 2x1 minus x0 minus x2 over x1, x0. L2. Yeah. Okay. Therefore, equation 2 here, this equation. Equation 2. In this special case, n is 2 and k is 1, is derivative of f at x1 is equal to f of 0 times derivative of L0 evaluate at x1 times this number. And then plus function value at x1 times derivative of L1 evaluate at x1. And then plus function value at x2 times this number. Then plus error term. Now n is 2. Yeah, this equation is for the loads that are equally spaced. Now let me Now in this example, I don't assume the loops are equally spaced. So let me call equation 2. This equation, actually, I have given a name to this equation. Should be equation 1, not equation 2. Yeah. Yeah, this is still equation 2. Equation 2 is for equally spaced loops. Here, I should change. What is equation 1 in this special case? Then plus the error, plus the error. It is a 1/3 factorial f the derivative sine x1 minus x0 x1 minus x2. So when n is 2 and k is 1, formula 1 is this. Now, second example, I assume the free rows are equally spaced. Example 2, assume x0 is x1 minus h. Then x1, x2 is x1 plus h. Then this equation, let me call this equation 3. Then equation 3 is, in this example, I assume the free rows equally spaced. Now I plug in those special x1, x2, and x3, x0, x1, x2 in equation 3. Then equation 3 is f derivative at x1 is equal to negative f x1 minus h times 1/2h plus f x1 plus h times 1/2h minus the error term, x1 minus x0, this is a h, x1 minus x2, negative h. So minus 1/3 factorial is 6. Then h squared. Then let me combine the first two terms. Then over 2 minus 1/, yeah. This formula is one of the formulas that we obtain while Taylor expansion. In the last 2 classes, I derived this formula from Taylor expansion. So from polynomial interpolation, we can get the formulas, at least this formula obtained from Taylor expansion. So this topic 1, I show you one example. Actually, we can derive differentiation, numerical differentiation formula for derivatives from polynomial interpolation. Yeah. This is a topic 1. Now, the second topic, we turn to section 2. Numerical integration. Numerical integration formulas are usually attained not from Taylor expansion, but from polynomial interpolation. Yeah. This is a topic 2. Topic 2. In this topic, we want to evaluate an integral from A to B. How to get formulas to evaluate this integral? By polynomial interpolation. Given a table of some function values, y f x0, f x1, f x2, f xn. The polynomial that interpolate this table, now this time, I don't use Lagrange form, but I use Newton's form. Okay, in Newton's form, the polynomial that interpolate this table is recall that this notation is divided difference notation. It is a constant, a number, times Q0 plus order 1 divided difference times Q1 and order 2 divided difference times Q2 and so on. The last term is order n divided difference times Qn. Where recall that Q0 is 1. Qi is x minus x0, x minus x1 times x minus xi minus 1. Right? Newton form. Okay. Newton form. The error term, okay. Function n, a general function. P polynomial, of course, they are not equal. To make them equal, we need to add error term, okay. Error term, error term, okay. Where error is equal to 1 over n plus 1 factorial, n plus 1. Sign depends on x, and then times w. W here is this is w. K from 0 to n product x minus sk. X minus sk. Okay. Where psi of x, it is in this interval AB. Yeah. Here, this integral is taken on this interval from A to B. And suppose the logs suppose all in this interval AB. Yeah. Suppose. Okay, suppose. Okay, now to get a formula to evaluate this integral, I take integral on this equation, then take integral on the equation. Then we have integral from a, b, f of x plus, is equal to integral from a, b, p, interpolation polynomial, plus integral on the error term, okay, on the error term. If I drop the error term, then we have a numerical formula to evaluate the integral. Let's consider some special cases. Okay, some special cases. Special cases. Number one is special case. Case is called trapezoid quadrature rule. Okay, trapezoid. Special case. Trapezoid rule. Trapezoid rule. Okay. In trapezoid rule, we said in this rule, we said n is 1, x0, x1, 2 rows. And said x0 is a, integral from a to b. Now, the first row is a. The second row is b, okay. Then, let me call this equation 4. Then equation 4 is integral a to b is integral on Newton interpolation polynomial. AB. Newton interpolation polynomial is f x0 times q0 x plus f x0 x1 times q1. Now n is 2. Yeah. And then plus error plus integral AB E1 because n is 1. Yeah. Okay, now in detail, x0 is A, x1 is B. So in detail, it is the coefficients are constant. So f x0 integral AB q0 dx. Yeah, I move out constant AB q1 and then error x0 is A. Divide the difference of a single point is function value. So actually, this is a function value and x0 is A. So this is a function value at A. Q0 is 1. This divide the difference by formula. It is f x1 minus f x0 over x1 minus x0 by formula. So this is a function value at x1. x1 is b. So this divided difference is a function value at b minus function value at a over x1 b minus a. Then integral q1. Q1 is x minus x0. It is a. Then plus the error. Now compare this integral and this integral, and then simplify the first two terms. Then we get the first two terms is b minus a over 2 f of b plus f of a plus f of b. This is the first two terms, and then plus error. Drop the error. Drop the error. We have trapezoid rule. We have trapezoid rule. Okay. Integral from a to b on the function f roughly is equal to b minus a over 2 f a plus f b. Yeah. The right hand side of this approximation is the area of a trapezoid. Let me draw the graph of function f. Function f. Suppose A is here, B is here, and this is the graph of function f. Then left side of this approximation integral is area of the region between the graph and x-axis and between A and B. Yeah, the integral is area of this region. Yeah, area of this region is integral. Then how about the right side? This is the area of the trapezoid. Which trapezoid? Yeah, this one. Join this point and this point with a line. Yeah. Right hand side, this number is area of this trapezoid. So trapezoid rule essentially says that use the area of this blue trapezoid to approximate the area of the region between the graph of the function f and x-axis and between A and B. Yeah, this is a trapezoid rule. Okay, now next, let me evaluate the error term. Okay. The error term in detail, it is E1 error. Let me see. This is En. N is 1. 1 over 2 factorial, second derivative at some point psi. The psi depends on x. X minus x0 a, x minus x1 b. Evaluate this. Okay. Because x minus a, x minus b is always negative over the interval AB, right? For any point, plug in any point in X, this product not greater than 0. Say, let me plug in A in X, then I get 0. Plug in B, I get X0. Plug in a point between A and B. X minus A greater than 0. X minus B less than 0. So for any point in this interval, for any X in this interval, the product not greater than 0. The product doesn't change sign. So by mean value theorem for integral, by mean value theorem for integrals, where this theorem is in my notes, it is a theorem 5.6. A theorem in lecture 5. By mean value theorem for integral, because this function doesn't change sign over the interval AB. So I can move on this guy outside the integral. Okay. So this is a 1 over 2 factorial constant moving on. And then I can also move this guy out. Move this guy out, then change psi x to some other sign. This sign is in this open interval. This sign guaranteed. It is guaranteed greater than A, less than B, times AB. This integral is computable. Compute this integral, we get negative. This function is less than or equal to 0, so negative. 12. Second derivative, evaluate example sign, then B minus A. This is the area term for trapezoid rule. So trapezoid rule. If you set h from x0 to x1, the distance between x0 and x1. Now in this case it's b minus 1. If you set h to be b minus a, then we get h to the. So trapezoid rule is an order-free formula. This is one special case. There were several other special cases. When we set the number of the rows to be free, then we get Simpson's rule. When we set n is 4, we get another rule. So basically, formulas for integrals, numerical formulas, they are usually come from polynomial interpolation. Let me stop here.